Our Earth is a fully charged, boundless battery. Just like our Sun, which is well known and understood to be an endless source of energy on which solar power depends, the Earth has a remarkably similar, renewable source of energy at its core that is both inexhaustible and ubiquitous. There are two heat sources originating from the Earth. The first is primordial. Radiating from the core of the Earth, it's as hot as the Sun and came from the initial formation of the Earth over 4.6 billion years ago. The second is radioactive decay from the naturally occurring elements of the Earth. This heat, this energy, can be accessed with the many geothermal technologies humanity has today, and even more so with the advanced geothermal technologies developed just in the last few years. From just one section of the Earth's crust, when using these geothermal technologies, there is enough energy to power all of humanity for hundreds of thousands of years. There are plenty of wonderful technologies which have been developed over the years to access and utilize this energy. This video will step through several of these technologies and how each of their designs work and where they're best applied. By the end, you will see how geothermal, when made scalable, will change our world. Geo-exchange, or residential heat pumps, are what many people first think geothermal is. While geo-exchange systems are very common and can be placed almost anywhere, they are not energy-producing systems. They require electricity, which is taken from the grid and used to power pumps, which pull heat from the Earth, just like using electricity to power an electric heater, but far more efficient. Traditional geothermal for direct heat use is a rarely used form of geothermal. It typically utilizes a hot, naturally permeable sedimentary aquifer, but sometimes can be done using igneous rock also. To produce heat, exploration is needed to find the right geological conditions, and wells are then drilled to extract brine. This style of geothermal is rare for two reasons. It needs the right kind of geological location, but that location also needs population density to consume the energy produced. A spa or hot spring is another type of geothermal many people think of. These are very rare instances of hot water from deep underground that flow to the surface along fault zones. These fault zones create natural pathways called fractures that allow water to flow to surface from deep underground. The connectivity of these pathways is referred to as permeability, the ability of fluid to flow through pore spaces or fractures in the rock. Where geothermal starts to really get interesting is when its energy is used to make electricity. Historically, traditional geothermal for electricity production requires a very hot hydrothermal source of water. Wells are drilled to extract brine from a naturally fractured reservoir, and then a heat-to-power facility is used to convert heat to electricity at surface. While it is a wonderful source of green and renewable energy, the subsurface conditions required for traditional geothermal systems are rare. It can be very difficult, time-consuming and costly to find and produce from these naturally occurring fractures. On average, the fractured zones do not have enough permeability to be viable for geothermal without intervention. Enhanced, or engineered geothermal systems, referred to as EGS, are new technologies growing in popularity, which could be used to increase the fractured nature of these low permeability zones. This allows for the permeability to be increased, thereby increasing the access to the hot rock. This is done by using hydraulic stimulation or fracking techniques. Alternatively, another type of EGS system uses thermal cooling of reservoirs by pumping cold water over long periods of time to stimulate and induce fracturing of a geothermal source rock. In situations where you have hot rock but no permeability, the intent of EGS is to fracture the rock and inject water into the formation, which flows through the fractures, then is pumped back to the surface for energy conversion. This technology is still being developed, but has the potential to make geothermal much more scalable while lowering the risk of investment. EGS is one of the few technologies designed to address geothermal scalability and could help take geothermal from the very rare to one day common. Several companies are working to bring this technology into operation now. It is important to remember that technological advancements making geothermal more scalable and widespread are central to the goals of all geothermal technologies. Accessing more and more of the Earth's natural battery, its energy, is going to be essential for geothermal to have a material contribution to the global energy transformation. All of the large-scale technologies we have covered so far still need some special, sometimes rare conditions to be viable. And most notably, all of these geothermal technologies are convection-based. For geothermal to be truly and globally scalable, to change our world, something more is required. Everloop is a conduction-based system and is designed to profoundly increase geothermal scalability. Conduction systems are the critical and key difference to enable geothermal from the rare to almost anywhere and everywhere on the planet. Here's how. First demonstrated in Rocky Mountain House, Alberta, the Everlight facility has been operational since December of 2019 and is the full-scale proof of the conduction-based Everloop design, proving that a sealed-off closed-loop system to harvest heat using pure conduction is not just doable, but truly viable. Think of the Everloop as a super deep, industrial-scale geo-exchange system. It provides highly predictable and reliable power, and the system can be tailored to the required output. This means the system is low risk and predictable. Additionally, using the thermosiphon effect, which removes the drawdown of a parasitic pump load, dramatically increases the efficiency of the system. It essentially provides more electricity to sell. Geographically, for a conduction-based system such as an Everloop, there are no special conditions required. Everloops can be placed almost anywhere. This means it's scalable. Ever's 1.0 design, also known as the James Joyce configuration, is the commercial version of the demonstration facility. It uses a single drilling location for both vertical wells, meaning half the surface footprint of the Everlight facility. Once at depth, the wells turn approximately 90 degrees and then split into multilaterals to create more surface area for the working fluid to be in contact with the rock, therefore increasing heat extraction and overall efficiency. Through advancements in drilling technology, Ever is developing a 2.0 design, angling the multilaterals deeper into the rock to greatly increase overall heat extraction. This means it's stackable, which allows for more scale and power at a single location. Ever can go anywhere, everywhere. This type of technology is boundless. Ever is continuously developing its drilling technologies and techniques to allow us to go deeper to reach hotter temperatures for a lower cost. Add that an Everloop is totally emissions-free, has a small and benign surface footprint, and several other features that we will get into next. We are now seeing a path to first diversifying energy, then transitioning and bringing change to our world. Let's look at what's generally inside a classic organic Rankine cycle heat-to-power facility. Here we see the hot fluid from the Everloop come out of the ground and go through a heat exchanger before going back into the underground system. The heat exchanger transfers the heat to a separate fluid, which when heated becomes a gas that turns a turbine generating electricity. From there, the fluid is cooled down and condensed back to a liquid state using an aerial cooler. It is then pumped back around to the heat exchanger in order to pick up more heat from the Everloop. The bigger the Everloop, the more heat it produces. So in some cases, more aerial coolers and turbines will be needed, unless there is a body of water nearby, which can also be used for cooling. Solar and wind are excellent examples of renewable energies, and so many of us now rely on these forms of power for our green energy needs. Being able to harness the sun and the wind to generate electricity was a big step towards a cleaner energy future for our world. However, these energy solutions have some drawbacks. While there is the obvious intermittency issue, as in power is only generated when the sun is shining or the wind is blowing, and then all the efforts going into battery technology to try and compensate for that, there is also the issue of the required surface land footprint. As can be seen here, an average solar farm with batteries requires up to 35 times the surface footprint for the equivalent baseload power generated by an Everloop, and wind requires another 4 times the land space beyond that. Regarding the intermittency problem, there is an opportunity here that only a conduction-based geothermal system can capitalize on: a flexible power output, or dispatchability. Everloop will actually pair very well with solar and wind because, as we all know, sometimes the sun doesn't shine and the wind doesn't blow. The Everloop system allows for dispatchability. a powerful and valuable energy generation characteristic. In this example, it can be seen that the same distribution and transmission infrastructure can be shared, a truly symbiotic green energy technology pairing. An Everloop can slow down and even pause its flow to allow the fluid to stay within the hot rock for a longer period of time and pick up additional charge. The Everloop can then ramp up and dispatch that higher temperature fluid on demand when the sun goes down or the wind stops blowing. For a portion of the day, Everloop can dispatch as much as 3 times its baseload rate. This means that Everloop is load following. So in the same day, it will always produce the full and total amount of power it was designed for, as if it were run constantly as baseload, but provided to the grid when it's most needed. Dispatchability of a baseload system completely solves the intermittency issue of solar and wind, something batteries will likely never really do, and pushes us all forward with renewable energy. Our Earth is a fully charged, boundless battery. We have the abilities and technologies to utilize this massive amount of energy literally just waiting right beneath our feet. Ever has a small and benign footprint. It is an emissions-free, predictable, baseload, dispatchable, and highly complementary energy source that is scalable globally. This will change our world forever. Energy forever.